Hello everyone, and welcome back to another free training video provided by CFDLand. In today's tutorial, we're going to tackle a classic and essential problem in aerodynamics, compressible flow in a nozzle using ANSYS Fluent. If you look at this slide, you can see the geometry we are working with. This is a converging-diverging nozzle. The shape isn't random. It is defined by the specific equation you see right on the screen. Area equals 0.1 plus square root of x, and x ranges from minus 0.5 to 0.5. We are going to simulate how air behaves as it gets squeezed through this restriction and then expands out the other side. This is a perfect example of compressible flow where density changes are critical. Now, before we jump into the setup, if you find these tutorials helpful, please do subscribe to our YouTube channel at the link below. Alright, let's get started with the simulation. As always, we start with drawing the sketch of our model. So I wanna drag a component of geometry into my workbench workspace and open Design Model software to begin. Before doing so, we need a database out of the points that we need to use in order to create this wall of our Convergent-Divergent Nozzle. So you already know that by putting different x values into this equation, we can have the other component. And in this column, you can see we used different points with a distance of 5 centimeters to each other. And this gives us these y values. And we can use these points to draw this curved line on top wall of the nozzle. But we need to convert it into Design Model template in order to use them later. So this is the template of the Design Model software. In column 1, we've got the group, then we've got the points, and then it comes the x value, and next column y value, and finally the z value. Of course, due to symmetrical shape of the nozzle, we are going to just model half of it and in 2D space. So there wouldn't be any z value. And then we know that you can use more points in order to create the curve. The more points that you use, the more accurate the geometry will be. So this 21 points represents this curved line above. This is all you need. But the point is that if you want to create the other lines, I mean, in these two vertical ones representing the inlet and outlet, and also the central axis, you need to group them in another one with 2 points. So here we go with the first point and then the other point, and do the same thing for the other lines. But this is not necessary. The most concern is about this curved one. And you can also copy just to group 1 into a txt file like this in order to use that for the software. So as you can see in here, I created this txt file and copied all the data in this, but including group 2 and group 3 and 4. So after doing it, you're free to get back to Design Model software to start. After pressing the X5 plane, following the Concept tab, you can find the 3D curved option. So from this type of definition from coordinates file, you're able to define and import a coordinate file for the software. By pressing this 3-dot button, you need to find this. And this txt file is my reference. And by pressing the generate button, you can see it is created. We just need to zoom a little bit to see that. So because I included group 2 to 4, we also see this vertical inlet and outlet and also the horizontal axis. So in total, in the triathlon, it shows us 4 distinct lines. And these all represents the boundaries of the nozzle. But we are not done yet. We have to convert it into a surface area because this is a CFD simulation and we are not working with edges. In order to do so, once again, following the Concept tab, you can see the surfaces from edges tool. what you need to provide for the software is just a closed curve for the software to group them together and find the space between them as the surface or our computational domain. Holding down the Control key, I select these four edges together and apply them. Without any thickness, we can generate that. And this represents a whole nozzle geometry. So before proceeding to ANSYS meshing, we need to suppress all these four edges together by right-click on this and suppress these bodies. So the only thing that we have and we want to transfer to ANSYS meshing is this surface body. Here we go with ANSYS meshing. So here we go with a meshing module. All right, I want to start my meshing node after clicking the mesh and changing the physics preference from mechanical to the CFD by the default element size that the software want to use. So it shows about 5 centimeters, and by pressing the generate, we can see what will happen. So it is mostly quadrilateral cells, which is our preferred choice for grid generation. But the point is that this is just two large elements and they cannot truly capture the behavior of a compressible flow that we expect to see in this nozzle. So we need to reduce the element size, and I'm going to do it on the whole face. So after pressing the face selection tool and selecting the whole nozzle surface, you can right click to insert a sizing. So there we go with a new actually submodel beneath the method and mesh, and the element size for this nozzle, for example, could be about 5 millimeters. And without any other change, let's just generate it. So, as you can see, this represents a very good and high quality grid, but we may see some triangles among the other quadrilateral cells, and this is not a desired choice because we try to have a fully structured grid, and this is possible due to simplicity of the model. Uh, so as another step, I want to insert a face meshing to the whole domain by pressing and selecting this face and apply this. You can see by default it's gonna use a map mesh and using quadrilateral cells, and this is all we know as a structured grid. So after doing so, you can see it has just turned into complete quadrilateral cells, and yeah, and it seems it shows a very good quality that we need to have a great convergence, because we're gonna include the compressibility effects. It is of the essence, and we have to follow this path. So in total, about 13,000 number of cells has generated, and we can proceed to the solver. But before doing so, we've got another mission in ANSYS meshing, and it is labeling the boundaries. So for a 2D space, the boundaries are the edges. After selecting the edge selection, we can start with this inlet. After selecting that, right-click to find Create Name Selection. Here we go with the name of it. I call this inlet. The other side represents the outlet. This is the wall of the nozzle, and we can simply call it wall. And finally, this is the central axis, and I'll call this axis. So in total, we can see 4 boundaries. And let's just now proceed to ANSYS Fluent. And this time, what I need is the Fluent launcher in here. And you can see we need to update this mesh to successfully transfer the generated grid into the solver. Very well. When it is checked, you can double click on Setup to open Fluent Launcher. First of all, do not forget to activate double precision. It will increase the accuracy by preventing the rounding off error, and it will calculate up to 16 decimals. And then based on your system configuration, employ the proper number of processors. So let's go with 4 cores. Very well. So we successfully imported the mesh, and let's just begin with general assumptions. This section simplifies the complex reservoirs so the computer can solve it. I want to begin by the solver type. This gonna be a compressible flow. We assume the air density changes. This is critical because in a nozzle, air moves very fast, often supersonic, which squeezes the air and changes its density. So we must use a density-based solver in this type of simulations in order to include the density changes. And then we've got the 2D space that must be set on axis symmetric. Instead of simulating the whole 3D round nozzle, we simulate a 2D slice of it. Because the nozzle is round and symmetrical, this gives the same result but calculates much faster. And finally, it comes the steady state solver because we are looking for the final stable flow pattern, not how it changes second by second. And we can just proceed to model section. So here we go with energy equation because there is going to be a high Mach number velocity of the air inside the nozzle. It is completely understandable that there is going to be a temperature change within the path. So we need to solve energy equation along the momentum equation. And more importantly, it's about the viscous turbulence model. Although ANSYS Fluent provides different turbulence models, our choice here would be K omega SSC turbulence model. So this is the best model for aerodynamics. It is very smart. It acts like one model in the free stream far from the walls of the nozzle and a different model near the walls. This makes it perfect for nozzles where the air friction against the wall is very important. And all in all, we can conclude SSTK omega model is the best one when it comes to this. So up to now, if you remember, we used density solver, but we didn't define anything for the density changes for the air or a working fluid. And this has to be done through the material section. So we already know that air is predefined and default material that is taken by ANSYS Fluent, and we're not going to change the material. But in case you want to add any other material, you're able and free to provide the properties of that along the create or edit button in this panel beneath the properties box. Or also use Fluent database in order to import widely used materials from the Fluent library. But for now, I just want to check the air properties as the default material of the software. As you can see in here, by default, software uses a constant density for the air, and this is not a correct approach when it comes to compressible fluids. Instead of this, I want to use an ideal gas approach. So this is the most important setting for compressible flow. It tells Fluent that density is not constant. It links density to pressure and temperature using the ideal gas law. As the air accelerates in the nozzle, pressure drops and density drops. If we leave density as constant, the simulation will be wrong and it will be incompressible fluid. So after changing the ideal gas, we can change and overwrite it in order to get to our next important step, which is the boundary conditions. So here we go with all labels we put on each boundary. I want to start with the inlet, which is the most important one. But before proceeding to its setting, I want to change the velocity inlet type to pressure inlet because what I have from the condition of our inlet is the pressure. And this is very important section. You have to pay more attention to this because the operating condition must be set also in here. So I put these two panels to explain what is going on in here. As you can see in here, software asks for a gauge total pressure and supersonic or initial gauge pressure in here. And this is where beginners get confused. We need to understand how ANSYS handles pressure numbers. So I want to begin by operating condition that you saw on the bottom here. So we need to define an operating pressure for the software before proceeding to gauge total pressure. What you need to know is that in ANSYS Fluent, the software doesn't usually calculate with absolute pressure. It uses gauge pressure relative to a reference point to avoid rounding errors. And you know that absolute pressure is the summation of operating pressure and gauge pressure. So we usually set this to an atmospheric, which is the default value that you can see in here, or 0 Pascal. Setting it to a low number like, for example, 500 Pascal means the gauge pressure numbers we type in the other panels will be very close to the actual absolute pressure. It's just a reference based on. So from now on, all gauge pressure that we set in here would be relative to operating pressure. And here we go with 1 atmosphere, and in terms of Pascal, it would be 101,325 Pascal. So imagine a huge tank of air attached to the back of this nozzle. This number is the pressure inside that tank where the air is not moving yet. It represents the total energy available to push the air. And then it comes the next field, which is the supersonic or initial gauge pressure. I want to put for this 98,000 Pascal. So this is the static pressure right at the inlet face, this boundary in blue color. And it has just two main reasons that we're doing so. First, it is the driving force. The air moves because of the difference between total pressure and static pressure. The gap between 1 atmosphere and 98,000 determines how fast the air enters the nozzle. And the next reason is the supersonic name that you can see in here. If the flow entering the domain was already faster than the sound, I mean it is in supersonic area, Fluent would use this number strictly. Since our inlet is likely subsonic slower than the sound, Fluent mostly uses this value as a starting guess to help the math converge. So then it comes the turbulence box down here because we do not have any data about the turbulence intensity, and because the ratio that must be set based on experiments, we leave them as it is and apply them. And next, in thermal tab, you have to set the total temperature of the air that is coming in. I want to keep 300 Kelvin and apply this as well. Next, it comes at outlet boundary condition, which has pressure outlet type boundary type. So, as you can see in here, once again, what software asks is the gauge pressure at this outlet that you can see in red arrows on the right side of the nozzle. So for this, once again, I want to put 5,000 Pascal. And once again, you know that it is relative to our operating pressure, which was 500. So for absolute pressure at this outlet boundary, we have 5,500 Pascal. And once again, we do not have any data about the turbulence effects and condition at the outlet, and we keep the default values. And the thermal tab, in case there would be any backflow, we consider 300 temperature for that. Of course, we do not expect any backflow when it comes to a converging-diverging nozzle. And this is just an assumption. And finally, it is the wall of the nozzle. We know that it's not moving, so it's the stationary wall. And more importantly, it's about the no slip shear condition. So the velocity remains 0 on the wall of the nozzle. And in thermal tab, you can see by default heat flux of 0. It means it's an adiabatic wall and there wouldn't be any heat transfer through this boundary. Alright, so I guess we're totally done with setup of this nozzle simulation, and now we need to delve into solution part. So I'm going to begin with the formulation that you can find on top. This is all because we applied density-based solver. We can see two distinct formulations. For the current simulation, we're going to use and employ the implicit formulation. So there are two solvers in Fluent when it comes to this. And the density-based solver is much better and more accurate because density and energy are tightly coupled. And for this, we're gonna use implicitly ROEFDS flux type. This is a specific mathematical scheme used to calculate how waves like shock waves travel through the fluid. It is very accurate for shock waves inside the nozzle. And then it comes the discretization methods, which is totally the matter of accuracy. First of all, for the gradient, we want to keep the least squares cell base, which is recommended for a fully structured grid, like in our case. And in the unstructured grids, you'd better use the green ghost node based. But for now, we keep the default one. And then for discretization of flow and rest equations, we want to keep the second order often. This is the most important one. This is somehow the momentum equation. But for turbulent kinetic energy and dispersion rate, we can decrease and manage the computational cost by applying first order often scheme. And then we've got the controls. So here we go with the current number. This is very important when it comes to compressible flows. Of course, in the current scenario, due to perfect grid that we generated, we do not need to change the current number, but this controls the stability. In a density-based solver, a higher current number helps the solution reach the answer faster, but it's too high, the calculation might crash. So for the current case, we want to keep the default values. By the way, if you want to know more about the current number, through the blog section on CFDLand website, you can find a comprehensive blog that can help you understand better. So let's proceed to a primary convergence criteria that you can find beneath the monitor section, residuals. Well, think of residuals as your simulation's way of showing you how well it's solving the equations. Every time Fluent runs an iteration, it's trying to solve equations for mass, momentum, and energy conservation. The residuals show us how much error is left in these solutions, basically how far we are from perfect conservation. When you start the simulation, these residuals usually start pretty high, but as the solution progresses, you want to see them dropping down. In most cases, we're looking for residuals to fall below 10 to the power minus 3 or even minus 4. This is like saying our error is less than 0.1%. By default, Fluent sets a specific convergence criteria for different equations. These are absolute criteria. Think of them as the finish line. When our residuals drop below these values, Fluent considers the solution converged. However, this is really important to understand. These default values aren't always what we need. For higher accuracy simulations, we might want to tighten these criteria. Now there's something really important I want to understand about convergence. You'll know your solution is converging when these residuals starts leveling off. They're not dropping anymore. But here's a pro tip. Don't just rely on residuals alone. It's good practice to also monitor things like mass flow rate or pressure drop to make sure they're stabilized too. Alright, so knowing what are these absolute criteria, we want to keep the default values and proceed. The thing is, as mentioned in the slides, we can not only rely on the residuals and we need to monitor a critical parameter ourselves during this solution. So this is where the report definition section comes in. If you want to define any report to monitor, you have to do it prior to start the solution from this section. For example, in our current case, the velocity or the temperature at the outlet could be a great choice. To define this, right-click and find a surface report. For example, different types. It could be an area weighted average type. And what I want to label it is the vel out or the velocity at the outlet. Then from these drop-down lists, you've got access to different parameters that you might need. For example, in our case, it comes the velocity. And then from surfaces box, I select outlet to measure the velocity on this specific boundary. You can do the same thing for any other variable. And this time, for example, it could be the temperature at the outlet. And at this time, this is the static temperature that must be measured along this solution, exactly on the outlet. So before starting the solution, we need an initial guess, and I want to employ the hybrid initialization and press initialize to have an initial one. So this is a smart guess for calculating the starting point. Instead of setting a single constant value everywhere that is done during the standard initialization, hybrid method looks at your inlet and outlet. It solves a very quick, simplified equations to create a smooth flow field that connects them. And in this way, you will have a more accurate solution which leads to faster convergence. And finally, from run calculation section, I define an appropriate number of iterations, for example, 500, to start the solution. So as you can see in here, it's not only the residuals plot. You can also see two reports that you define, and as soon as they reach a constant value, we can ensure the stability and convergence to stop the solution. With a pop-up information about the completion of the calculation, you can see automatically the solution is stopped after about 350 iterations. As I said, we cannot only trust the residuals plot, and we need to check the critical parameters. So here we go with the velocity at the outlet. We can see it has reached the constant value that we were looking for, and these two guarantee that it's time to check the results of our simulation. So I want to begin by, let's see, we've got the graphics in here, and the most important tool is contours. So in this panel, all you have to set is the variable that you're going to measure. For this converging-diverging nozzle, maybe the velocity comes first. Then you have to select which boundary you want to measure and display the velocity magnitude on. For example, because I want to see that over the whole domain, I do not need to select either of them. So simply press Save or Display button, and what you can see is the velocity distribution along the whole nozzle. Before analysis, I guess it's not a bad idea to have a complete view. From the View tab and then Views, you can find the axis, the mirror plane. And by applying that, from now on, you will have the other symmetry. So what can be seen in here is the velocity that starts with low values that you can see in blue color at the inlet, increases slightly in the converging section, and then rapidly shoots up maximum in red in the diverging section. This confirms the flow has gone supersonic. If we check the values, we can see at our maximum, this airflow experienced about 600 meters per second velocity magnitude. In the converging part, the flow is subsonic. Mach number is below 1. You can also have the Mach number display from here. And right now you can see the values that are in blue is about the minimum one, less than 1. And this represents the subsonic flow. As the area gets smaller, velocity increases, and at the throw, or the middle part, the flow likely reaches Mach number of 1. That can be seen about green color. So finally, in the diverging part on the right side, because the flow is supersonic, expanding the area causes the velocity to increase further, unlike subsonic flow where expanding slows it down. And at its maximum, it experiences about 600 meters per second. Since the speed of the sound is roughly 340 meters per second, depending on the temperature, we have reached approximately Mach number of 1.7 or 1.8. And this all represents that this gonna be a supersonic flow in the nozzle. As our next move, we can display another parameter like the temperature and also the density that we expect the same pattern but with different values. Yeah, exactly. So what can be seen in this temperature contour is that once again at the inlet we have the red area, the highest values, and at the outlet we have the cold flow. So this proves the conservation of energy. Total energy is constant. As the air accelerates, kinetic energy goes up. the thermal energy or temperature must go down to compensate. So this significant drop in temperature from 299 or let's say 300 Kelvin to its minimum, which is about 110 Kelvin, shows how much energy was converted into a speed. And the same pattern that can be seen in the density display. And the density is high at the inlet and it drops significantly at the outlet. And this confirms our ideal gas setting is working perfectly. If we had used constant density, this plot would be one solid color without any change. And as the flow accelerates and pressure drops in the nozzle, the gas expands, reducing the density remarkably. So as we can see, the physics are perfectly captured. The inverse relationship between velocity and temperature is clear. As velocity expands into diverging section, supersonic acceleration, the density and temperature drop drastically to satisfy the conservation law. This validates our density-based solver and ideal gas setup. As the last step in our analysis, I want to show you a quantitative value. So you may find the plot section down here and then XY plot. In here, we've got the same settings similar to the panel of contours. The only difference is the plot duration. So I need a line to measure the velocity along it, and we already have the axis in the middle of the nozzle, and I can use it. So on my y-axis of plot, I want to get the velocity magnitude or, for example, Mach number, and then from surfaces, we can simply pick up the axis. The plot duration must be along the line direction, and it is clearly along the x-axis. So simply you can plot the Mach number variation along the center line. Look at this beautiful smooth curve. It perfectly validates our setup. We start subsonic and hit exactly Mach number of 1 somewhere around the 0 point in the throat or the middle part of the nozzle, and then continue to accelerate theoretically perfectly to Mach number 2.5 at the outlet. This implies no shocks inside the nozzle and a perfect isentropic expansion that is happening through this.